In this video, we're going to talk about the factors that affect the oxygen-hemoglobin dissociation curve. Hey, what's up you guys, and welcome back to my channel. So last video, we introduced the structure of hemoglobin, how oxygen binds to hemoglobin, and a concept known as the oxygen-hemoglobin dissociation curve. And if you missed that video, then I'll link it up in the description below. But today, we're going to build on our fortress of knowledge. We're going to talk about the factors that affect the oxygen-hemoglobin dissociation curve and therefore affect the binding of oxygen to hemoglobin. And as always, this information is going to play a big role when we start to talk about pathology. So grab your thinking cap and some coffee and let's get started. Okay, so last video we introduced the concept of the oxygen-hemoglobin dissociation curve. Now let's talk about the factors that can affect this. So let's look at the curve really quick. Okay, so here you have pictured the normal oxygen-hemoglobin dissociation curve. If the curve shifts to the right, then oxygen is more easily released from hemoglobin, and hemoglobin is not as saturated with oxygen. But if the curve shifts to the left, then oxygen stays on hemoglobin more, meaning it's less easily released. Oxygen clings on to hemoglobin. So it's kind of like that clingy boyfriend or girlfriend that you might have. Okay, moving on. So things that can shift the curve include temperature, pH, CO2, and diphosphoglycerate, also known as DPG. So things that can shift the graph to the right include increased temperature, increased CO2, increased DPG, and decreased pH. And things that can shift the graph to the left include decreased temperature, decreased CO2, decreased DPG, and increased pH. Okay, so let's take a closer look at these now, starting with temperature. So let's remember our cellular respiration formula. Glucose plus oxygen yields carbon dioxide, water, ATP, and heat. Now heat is what we care about when we are talking about temperature. So if a cell has a higher metabolic rate, the cell produces more heat. And heat will reduce the affinity of hemoglobin for oxygen, which means that more oxygen is released from hemoglobin. More oxygen will go into the tissues, that way they can continue metabolism. So an increased temperature means more oxygen release, which means hemoglobin is less saturated with oxygen. But the reverse is also true. At cooler body temperatures, metabolic rate slows. This decreases heat production and the curve shifts to the left. Hemoglobin will hold onto oxygen more and will be more saturated with oxygen. So now let's talk about carbon dioxide. Again, carbon dioxide is a byproduct of metabolism. An increased carbon dioxide level is a product of an increased metabolic rate. An increased metabolic rate means that we need more oxygen. The curve will shift to the right and more oxygen will be released from hemoglobin, meaning that hemoglobin will be less saturated with oxygen. But if there is less CO2, that is a product of lower metabolism, which means there is less oxygen need. The graph will shift to the left and hemoglobin will be more saturated with oxygen because not as much oxygen will release from hemoglobin. Now when we talk about DPG, nurses, bear with me. This is the one and only time I have spoken about DPG in my nursing education and in my nursing career so far. So let's just learn this concept for our phys classes. DPG is a product of anaerobic metabolism. More DPG means that we need more oxygen. And this makes sense, right? because we're going through anaerobic metabolism, and anaerobic metabolism occurs without oxygen. And when anaerobic metabolism occurs, our body is not efficient. So we need that oxygen, that way we can switch to aerobic metabolism. So if we have more DPG, we need more oxygen. The graph will shift to the right, and the percent saturation of hemoglobin will decrease. More oxygen will be released to cells. But no DPG means that the graph will shift to the left. If there is no DPG, then we may not be undergoing anaerobic metabolism, which means we might not need as much oxygen, which means hemoglobin will be more saturated with oxygen. Now, fun fact here, DPG is produced in chronic hypoxia by red blood cells. And examples of conditions which might produce DPG include anemia and high altitudes. So we'll talk about this in more detail later, but hydrogen ions actually decrease pH. The more hydrogen ions that you have in your body, the lower your pH will be. Anaerobic metabolism will produce lactic acid, which will increase the load of hydrogen ions and decrease our pH. At a point of maximal exertion, a lot of hydrogen ions are produced. This will decrease pH and shift the graph to the right, which means that oxygen will release more easily from hemoglobin. And I think that this makes sense because remember, anaerobic metabolism is not very efficient, and we need all the oxygen that we can have to shift back into aerobic metabolism. But the reverse is also true. Less metabolism produces less hydrogen ions, and less hydrogen ions means that we will have a higher pH, and a higher pH means that the graph will shift to the left. And a left shift on the graph increases the saturation of hemoglobin, and oxygen will cling on to hemoglobin more. Now, normal body pH is 7.35 to 7.45, with a perfect pH right in the middle at 7.4. At a pH of 7.4 and a PO2 of 40 millimeters of mercury, hemoglobin is 75% saturated. However, if pH drops to 7.2, which is lower but still compatible with life, hemoglobin saturation will drop to 63%, and 12% more oxygen will be offloaded from hemoglobin. And the hemoglobin curve shift due to pH change is called the Bohr effect. Alright, so the last thing that we should talk about are the differences between fetal hemoglobin and adult hemoglobin. So babies have a special type of hemoglobin, that way they can survive in the low oxygen environment with the placenta. Their hemoglobin is actually structured differently. It has gamma chains instead of beta chains that adults have. And the gamma chains give oxygen a higher affinity for hemoglobin, which means oxygen does not want to release from hemoglobin. And also it means that at a lower PO2, hemoglobin is pretty saturated with oxygen. And this is good because the PO2 in the placenta is low, so babies will have an extra oxygen reserve. Think about fetal hemoglobin as a left shift on the oxygen-hemoglobin dissociation curve. Hey guys, welcome back. So I hope that information made sense to you. If you got value out of this video, then tap the like button. If you have any questions, feel free to comment down below. Share your favorite videos and subscribe for more content. Stay safe, and I'll see you guys next time.